Hello everyone, my name is Pascal Jörke and I am a PhD student at the Communication Networks Institute of the TU Dortmund University in Germany. Today's talk is called From LENA to LENA-NB, Implementation and Performance Evaluation of NB-IoT and Early Data Transmission in ns-3, in which I will present our latest performance comparison between different NB-IoT transmission modes in highly scaled IoT networks. This talk is organized as follows. I will start with a short motivation on the scalability of IoT networks and then explain some NB-IoT fundamentals for better understanding of the following results. For our performance analysis, we have implemented the NB-IoT technology in ns-3, which is why I will give a short overview of the implementation, which is then followed by the performance comparison of the legacy transmission mode, Cellular-IoT optimization mode, and early data transmission, which has been introduced in 3GPP release 15. And finally, this talk will be concluded. So let's start with an overview of the challenges of low power wide area networks in the context of Internet of Things applications. The main requirements of LPWAN networks are energy efficiency for long battery life of small battery powered sensors, followed by robust signals for long transmission ranges and deep indoor penetration of signals, as well as a high scalability to support a massive number of devices. This work will mainly focus on the massive scalability, and when we take a look on the global IoT connections forecast for the next years, the load on the networks will drastically increase. That's why the design goals of NB-IoT networks has been adapted from 60,000 devices per square kilometer in 3GPP release 13 to 1 million devices per square kilometer in 3GPP release 15. This support of a massive number of devices requires a reduced signaling overhead for each data transmission, which does not only affect the network capacity, but also has a direct impact on the energy efficiency of the devices for an even better battery performance. So let's take a quick look on the power saving techniques in NB-IoT. To address the challenge of a long battery lifetime, NB-IoT introduces two new features called Extended Discontinuous Reception, short EDRX, and Power Saving Mode, short PSM. When the device has transmitted or received data in connected mode, it switches to idle mode. With EDRX, paging occasions are more relaxed and the device can remain longer in a power saving state between these occasions. After a time defined by the timer T3324, the device switches in a power saving mode where the device shuts off its modem and becomes unreachable for the network, but is still registered. This enables a very low power consumption for a long battery lifetime. When the device needs to transmit data, it wakes up and resumes its session by reconnecting to the base station. The device also needs to wake up after the timer T3412 expires in order to perform a tracking area update. For a maximum battery life, the time spent in PSM should be as long as possible. Since the device's power consumption is the highest in the connected state, this state needs to be as short as possible, thus making the reduction of signaling overhead mandatory. In contrast to power saving techniques is coverage enhancement. With LTE, a maximum coupling loss of about 141 decibels is achievable. When using the Okumura-Hata channel model with 15 decibels additional basement penetration loss, this results in a 1 kilometer basement penetration range, which is insufficient for most deep indoor IoT devices. With LTE-M, a design objective of 156 decibels of maximum coupling loss has been defined, extending the basement penetration range to up to 2.3 kilometers. NB-IoT extends the maximum coupling loss finally to 164 decibels and enables a basement penetration range of 3.8 kilometers, which is more than 4 times the range of LTE. This is mostly made possible by using message repetitions. NB-IoT can repeat its messages up to 128 times in uplink direction and 2048 times in downlink direction, which increases the energy per bit and reduces the bit error rate. But with repeated transmissions, the time on air increases drastically, which then reduces the battery life of the devices as well as the spectral efficiency, which is why the number of repetitions as well as the number of signaling messages should be as low as possible. When we talk about spectral efficiency, we talk about data being transmitted in a specific time and a specific bandwidth. When we look at the signaling overhead of a single user transmission, in this case a co-op UDP-based transmission along with an application layer acknowledgement, we can see that this single user data transmission needs 23 user-specific transmissions in total and therefore gives the transmission a poor spectral efficiency. In NB-IoT, this transmission overhead needs to be reduced as much as possible. That's why in the first attempt, Cellular-IoT C-Plane Optimization has been introduced. With C-IoT optimization, user data are piggybacked in the message 5 of the RRC connection resume procedure, and this don't have to be transmitted in a separate message, reducing the overall number of user-specific transmissions from 23 to 21 messages, which is still a poor spectral efficiency. That's why in 3GPP release 15, the early data transmission procedure has been introduced. Instead of an RRC connection resume request message, which is message 3, the UE can send an early data request message with piggybacked user data. In the responding early data complete message, downlink data, such as the application acknowledgement, can be piggybacked. This procedure complements the legacy NB-IoT connection procedure and reduces the overall number of user-specific messages from 23 to only 8 messages, which is a huge impact on the spectral efficiency and therefore on the energy efficiency. But what is the impact exactly on the user and network performance? To answer this question, we have implemented NB-IoT in ns-3, whose source code to ns-3 LENA-NB is publicly available on GitHub. Since NB-IoT is derived from LTE, we could work with the existing source code. However, for the NB-IoT random access procedure, we had to perform major changes on the MAC and PHY layer to include different coverage enhancement levels. Additionally, to integrate the new RRC Resume procedure as well as the early data transmission procedure, we also needed to modify the RRC layer to comply with the new procedures. For evaluating the energy efficiency, a novel energy state machine was implemented, which include the new power states EDRX and PSM. Finally, since NB-IoT uses transmission gaps and cross-subframe scheduling, a new basic scheduler was implemented, which is able to schedule up to 2048 consecutive subframes with additional scheduling gaps. Due to time limitations, I can't dive into each detail of our implementation, but I will briefly give an overview on scheduling in NB-IoT. Due to relaxed timings and half-duplex operations, DCI and data are scheduled in different subframes. For processing time, as well as downlink uplink switches of the transceiver, additional transmission gaps are introduced between downlink and uplink. As a consequence, the UE might miss some DCIs, which needs to be considered when scheduling UEs. With up to 2048 repetitions, up to 2048 subframes must be reserved for a single UE, along with additional transmission gaps for serving other devices during this gap. Finally, in uplink direction, so-called resource units are used instead of a subframe, whose length depends on the number of subcarriers used for the uplink. Note that currently only singleton transmissions are supported, which means that only one subcarrier with 15 kHz is scheduled per device. To ensure a correct implementation of the message flow, we used an Amarisoft E0B and EPC along with a Quectel BG96 device and logged acknowledged uplink transmissions, which gave identical message traces compared to our ns-3 simulations. But now let's talk about results. Using this framework, we have performed extensive simulation of different transmission modes and network densities. Each simulation ran for 15 minutes simulation time, including 5 minutes of pre-run, where devices are scheduled in empty cells and experience best, but unrealistic spectral conditions. The intermediate 5 minutes are used for this performance evaluation, while the last 5 minutes schedule new devices to keep the channel busy and letting the intermediate devices complete their transmissions. The cell size is based on the average cell size in the city of Dortmund, Germany, which is 2.5 kilometers diameter for 4.91 square kilometers cell area. As a channel model, WinR Plus is used with additional indoor and deep indoor attenuations. Outer, indoor, and deep indoor devices are distributed equally over the cell area. As a payload at UDP layer, 32 bytes 5G MMTC application payload is used along with 4 bytes CoreUp header and 13 bytes DTLS header. Let's take a look on the results. On the left side, you can see the results of the end-to-end latency in milliseconds. On the right side, the packet delivery ratio is given in red. After each simulation run, the number of devices is increased. The increase of latency is as expected, since an increased number of devices results in an increased competition for resources. Note that in high-density scenarios, EDT provides 3 times better latency than the standard transmission mode, since user data are already sent in message 3 and does not require an RRC release procedure. The packet delivery ratio is high in all scenarios, with only a minor drop in the largest scenario with 170,000 devices. Next, we take a look at the energy consumption and the resulting battery lifetime. Again, EDT increases the performance in terms of a low power consumption and a long battery life, giving up to 1.6 times longer battery life. Since the devices remain most of the time in PSM, the impact of energy performance is lower compared to the latency, but still noticeable. The small drop in packet delivery ratio leads to the question if the capacity limit is already reached. To answer this question, we firstly evaluated the spectrum usage in downlink direction. We can see that downlink broadcast already occupies 30% of the available resources, which is the first indicator of a possible bottleneck in the downlink. Note that the spectrum usage is stacked from below to top, but the upcoming user data are not added on each other. The results show that while EDT uses mostly 4 times less spectrum, all transmission modes leave plenty of room in the spectrum for more devices to join. So with this number of devices, the downlink spectrum is no bottleneck yet. When we take the number of random access collisions into account, we can see that very few random access collisions occur in cells with up to 10,000 devices, but rapidly increase in the largest scenarios, which implies a saturation of the available random access windows. When the device fails the random access, it retries several times. Overloaded random access windows then lead to more and more random access retransmissions, which overload the random access windows even more. So for an even better scalability, the random access parameterization needs to be optimized for small data transmissions. Okay, so let's conclude the result of today's talk. In the next few years, billions of IoT devices require access to communication networks. Therefore, communication networks need to be designed for massive scalability. To face this challenge, 3GPP has introduced in NB-IoT release 15 a new transmission mode called early data transmission, which promises a better spectral efficiency along with a better user performance. To evaluate its performance compared to legacy transmission modes, we have implemented NB-IoT for the ns-3 simulation framework and provided a first NB-IoT performance comparison. The results show that EDT provides 3 times lower end-to-end delay, along with an 1.6 times better battery life than legacy NB-IoT transmissions. Additionally, EDT uses 3.7 times less downlink spectrum, but is equally limited by the used random access window configuration. Still, all transmission schemes have shown good scalability, which can be extended with further optimizations on the radio resource configuration in terms of optimal random access window user data ratio, along with using non-anchor carriers for additional resources. All in all, EDT is highly recommended and should be used as a default transmission mode. Next up, we work on performance optimization in terms of shorter computing time for large-scale scenarios, since simulating large scenarios sometimes takes days to compute, even on high-performance simulation servers. Additionally, more NB-IoT features such as non-anchor carriers, multi-tone transmissions, as well as pre-configured uplink resources may be implemented in the future. Thank you for your attention and feel free to contact me if you have any questions.